Okay, so this is the second lecture on the finite volume method, and we'll start from where we left last time. So we had a problem of this kind where we had this 1D problem where we discretized, or rather we had the governing equation, which was the uh, which is basically the 1D heat diffusion equation, steady state heat conduction equation, with some sources, and the problem has to be solved in a one-dimensional domain. So we discretized our system in the finite volume method. We created a volume, and we looked at integration of this governing equation on a small finite volume. And subsequently, we reached this equation where we could write the temperature at any point P in terms of its neighboring values, uh, an unknown value or a constant value B. And what we came across during this process was that these coefficients AP, AE, and AW are actually dependent on the interface conductivity. So here KE and KW, and AP, which is the coefficient of the nodal value point on the node P, is can be written in terms of this variable, or can be written as AE plus AW minus SP delta X, where we have used the concept of linearization of the source term S. So if you remember, in the last class we spoke about two important aspects. So we spoke about that we need solutions to be physically realistic. So essentially, when we solve our differential equation, or when we solve our discretization equation, we need solutions which are physically realistic. And the second aspect that we wanted to achieve was to have an overall balance. Okay, so what I want to discuss today is how do we do these, how do we achieve both of them, and what are the conditions, or what are the rules that we need to consider to essentially obtain both, or to satisfy both these aspects. So we look at the basic rules that will help us satisfy these two key aspects. So in finite volume method there are four rules. So let me introduce each rule at a time. So we'll go by rule 1. The first rule, essentially, if I can summarize, it talks about in terms of consistency at the control volume phases. So what it says is something like this. If you look at the 1D problem, right, and let me just say that the node P is here, node W is here, and the node E is here. So we spoke about a flux crossing this phase E, right? So let's say this flux is, let me say it's given by 1, whatever that expression may be. And when we go to node E, we will also see a flux coming in. Let's say that is 2. Okay, so 1 is essentially heat flux leaving, which is leaving the cell surrounding point P, and 2 is the heat flux entering the adjoining control volume. Okay, so the rule basically goes as such that it says that when you have a phase which is common, so in this case E, so when we have a common phase, when the phase is common to two CVs, or to two adjacent CVs, then the flux in both CVs at that phase, the flux must be represented by the same expression. in both CVs. Okay. Now, why do we say that it should be the same expression? Well, it's logical that conservation of flow of heat would actually essentially mean that heat flux leaving one CV should be equal to heat flux which is entering the neighboring CV, right? But then let's say to explain this whole idea, let me say that the flux leaving a QI, the flux Q1, which I'm denoting here, right? This flux, let's say I write this as, so we know it is going to be KE TE minus TP by delta XE, where delta XE is this distance, right? So let me just say that I want to represent that the property or the interface conductivity, let me say that I sort of have an approximation for KE, and I'm going to say that this entire, because remember we have eventually, the reason I'm coming down to this is we have values only at the nodal locations. So to approximate KE, I could actually say that the conductivity of this entire cell, right, is approximated. So I could say KE is approximated by the nodal value in that cell. Okay, so what that would mean is that QI could then be written as KP T minus TP by delta XC. Okay, so what it means is we are approximating the conductivity at interface E by the upstream conductivity or the upstream nodal conductivity. Now in that same way I can now write Q2. Q2 would be the heat flux entering into the adjoining control volume. That should be written as, then by the same logic, that would become equal to KE TE minus TP, sorry, minus TP by delta XE. Now if I say that for basic conservation, if QI is, if Q1 QI or Q1 is the same as Q2, it would essentially mean that KP would have to be equal to KE to accomplish this, for this to be true, or for this to be valid. Right? So the only way now I can also do the same thing on the upstream side, on the W phase, and I can say that essentially the only way this approximation, that approximating conductivity in the cell, in the nodal value of conductivity for the interface value will only work when you have a uniform conductivity material. Okay, so otherwise what we will have is a mismatch of flux coming in and going out. So hence the interface flux must be considered with care, because it would actually impact your calculation on both sides of the cell, of the control volume. So that is rule 1, okay, which essentially talks about keeping the condition consistent. Rule 2 talks about, we can say it talks about this positive coefficients in our discretization equation. So we've been writing our discretization equation as APTP to be AETE plus AWTW plus P, and I could actually, this is basically a 1D equation, right? But I could say that in higher dimensions, let's say 2 or 3 dimensions, this equation should become APTP as A and B, T and B plus B, where NB are now the neighboring nodes, all the neighboring nodes. So essentially you're summing over all neighbors, right? Now, in most situations that we will encounter, the value of the dependent variable, so in this case the value of dependent variable would be basically temperature Tp, will be influenced from the neighbors only through convection and diffusion. That is what we are doing in this course actually. So if there is only convection and diffusion which can cause a substantial impact on the nodal values, right? What it means is that if I was to increase the nodal values by some constant, let's say if the nodal values were increasing, they don't have to necessarily increase by same constant, but let me say that the neighboring value was maybe to increase by some constant. So it could be one neighbor, it could be all neighbors, it doesn't matter. And even the constant doesn't have to be same for all neighbors. But what I'm trying to refer to is that if the neighboring value increases by a constant, then clearly the value of the temperature should, the nodal point Tp should also increase, right? So if C is greater than 0, clearly Tp should also increase, and it should not decrease, right? Which means the only way this can be true from this equation is that if the coefficients AP and all neighboring value coefficients have the same sign. So essentially, then basically what you mean is what will happen is that if you increase the temperature value T in any neighbor value by some constant C, clearly the effect will be felt in P and the nodal value at P, and the temperature there would also increase. Okay, so what we'll do in this class, and what is basically the terminology which is even used in Patankar's book, is that you choose to write the governing equation in such a way that AP is always greater than 0, which means since AP is greater than 0, A and B should also be greater than 0. So we will try and write our equations in such a way that these coefficients are always positive. So the second rule, if in a nutshell, says that all coefficients, so AP and A and B, should be greater than 0. That is the second rule. That if we maintain this rule, we will get physically realistic solutions and overall balance. Okay. Now clearly one may say that what if AP is greater than 0 but some one of the A and B's or the neighboring coefficients are not 0? Then we will have a physically unrealistic solution. And we'll see in later when we do some problems here, you will see that it leads to an unrealistic behavior. Now let's go to the third rule. The third rule talks about the source term, and this can be written as negative slope linearization of source term. So if you go back to what we had done earlier, so if I can just go up a bit. So we had this equation for AP, right? We had AP as AE minus AE plus AW minus SP delta X. So let's take this equation again. So we have AP is AE plus AW minus SP delta X. Now clearly we said that even if, and remember AE was KE by delta XE, AW was KE W by delta X W. So clearly AE and AW are both positive numbers. But the second rule says that not just the neighbors, the coefficient itself. So the coefficient of the nodal value which we have, on which the equation is being written, which means P, even AP should be greater than 0, right? But AP, as we see, is AE plus AW minus SP delta X. So this SP, right, AP can still be less than 0 for some values of SP. The only way AP will be non-negative is if we require, so AP will be non-negative if SP is less than 0. Right? This is the essence of the third rule. And this is what I meant by negative slope linearization, that we ensure that the slope value, the SP value, is always negative in the source term. Now, this may seem a bit arbitrary to some people, but there is a quite physical justification for this. Note that if SP is greater than 0, this means that TP would actually be increasing as the source term increases. Now, if TP increases, this will lead to a higher value of S, the heat generation rate, right? This will lead to S increasing, which will lead to again TP getting increased. If you recall that S is essentially, or S bar is SC plus SPTP. So clearly, this would basically result in a vicious increase in temperature, and rather an uncontrolled increase in temperature, which is physically unrealistic. So to avoid that situation, we will ensure that when we linearize a source term, we will always, in our numerics, we will ensure that SP is less than 0. Now, how do we do this is something which we'll discuss in the next lecture. Okay, now we get to rule 4, the final rule. Now this rule is about, or is called as sum of neighbor coefficients. So let's say we are solving a linear equation, a linear differential equation. Okay, a basic example of a linear differential equation would be that we're solving for, let's say, d by dx of k dt dx is 0, right? Or it could even be with the source term, which is a constant, is independent of temperature. Okay, so clearly for linear problems, if t is a solution, then t plus some constant should also be a solution. So both can be solutions. Right? And if I look at my discretization equation, if we look at that equation, right, it's clear that if T plus C is a solution, so if I increase the temperature everywhere by the same amount, right, that should translate to the nodal value also increasing by the same value, by the same amount. In other words, if say the temperature is uniform everywhere, and that's the solution of the problem, and let's say I increase the temperature by a small amount everywhere, then the nodal values or the discretization equation should also reflect the fact that the temperature has increased by the same constant value, which means that the coefficient AP should actually be a summation of A and B for linear problems, right? So this is almost, as I'm saying, this is almost as saying that if the source term is absent, right, and the neighbor temperatures are also the same, essentially we should have TP to be equal to TNB, which implies that AP should be summation A and B. Okay, so as long as we can maintain these four basic rules, we are guaranteed of getting physically realistic solutions with overall balance. And so when we develop our equations in this finite volume method, we will try and ensure that we have taken these aspects into these four rules into consideration. Now there are a few important aspects about this which I should emphasize. One of the important aspects that I have not spoken about in detail, but we will do when we'll see it in more detail as we go along, that it is not necessary that delta xw should be equal to delta xe. If it's equal, then basically what we are leading to is a uniform grid. But if it's not equal, right, if delta xe is not equal to delta xw, then essentially if we draw the grid, this is point P, this is E, and this is, let's say this is W, then we're saying this is delta xe and this is delta xw. So if delta xe and delta xw are not equal to each other, then what we are getting is a non-uniform grid. And sometimes this non-uniform grid is desirable. There's a reason for this, especially when you look at the temperature versus space dependence. If the T versus X dependence is steep, so there's a large change, let's say, in temperature over a small distance, then you would rather have a finer grid in that region to be able to resolve the large gradients in the temperature and to get better accuracy. Now the issue is that if we have a steep gradient, then we should be ideally we should be taking a finer grid in that region. But a priori or beforehand, we will not know where we need a finer grid and where we need a coarse where we can do with the coarse grid. So this T versus X variation is not known before the problem is solved. So what is the solution, or what is the remedy? So what we can do is, in this scenario, we can first obtain very preliminary coarse grid solutions. So preliminary coarse grid solutions. These could be solutions which can be obtained with a coarse grid which is uniform, non-uniform, it doesn't matter. Okay, but this coarse grid solution could be used to identify regions where the temperature versus X dependence is extremely sharp, and maybe regions where it is not even, where it is, where the temperature varies very slowly with space, and where we don't need to worry about high resolution. Now once we have this preliminary grid T versus X variation, or this preliminary solution, we can then construct a suitable grid, a suitable non-uniform grid, right, to obtain higher accuracy solutions. This is a standard practice in all computation research, that you first obtain some understanding of how the solution would look like, and then you refine your grid to be able to attain a better, more accurate and a more reliable solution. Now one of the key aspects here is that if we have to obtain or we have to make a judgment based on this coarse grid solution, it is extremely important that this coarse grid solution also be physically realistic and physically meaningful. And that is the reason we spoke about, getting physically realistic and overall and solutions which have which give you an overall balance. Okay, so if we can maintain overall balance, and if we can maintain physically realistic solutions for any type of grid, then this is fairly easy to obtain, or is fairly, we can have confidence on this exercise. The second aspect which we need to worry about, and which we have not looked into in great detail, is how do we choose the conductivity at the interface conductivity. So, because note that if k is not constant, so if k is either temperature dependent, right? K could be either temperature dependent, or k could be space dependent, or it could be both. So k could be temperature dependent because we can have a homogeneous medium in which the conductivity changes with temperature. And k could be varying with x because we may have a non-homogeneous or a non-homogeneity, okay, in the material. This is typically true when we have a composite slab. By a composite slab, I essentially mean that we can have two materials in contact with each other, right? So this could be material A and this could be material B. This is B, this is A, and so Ka and Kb are not equal, right? So they are two materials which have been joined together. Okay, so since we will have values only at nodal points, so K, for example, if Ke is to be determined and I only know values at Kp, Kw and Ke, then I need to find some suitable form in which this could be accomplished, right? And it doesn't have to be limited to this. Actually, the schemes could be even more extensive, but this is the idea that we should be able to write our interface conductivities as some function of these nodal values. So the question is, how do we choose these values, or how do we decide what should be the interface conductivity? Okay, so let's look at the most simplest option. Okay, so let's say we will look at two different options. Not that there are only these two methods which are possible, but let's say if I go back to the grid, so we have point P, point E, right? And let's say with the control volume face is somewhere, I don't know where it is, that we'll discuss later. So the distance between these 2 points is delta xe, right? So just for nomenclature, this is the face E. Let me choose to say that the distance of the face E from E is represented by a distance delta E xe plus, and the distance of E from P is represented by delta xe minus. So the easiest approach, or the first approach that I'm trying to look in or trying to show you, is that we could assume a linear variation of k between the points P and E. Okay, now what it means is that we could now write, using a simple lever rule, we could write that k at E is some function of distance, right? So we'll have a fractional value of distance here. So let me define a fractional distance or an interpolation factor. Let's say this is an interpolation factor Fe to be delta xe plus by delta xe. So let's say delta xe plus was 0, in which case point E or the face E coincides with capital E, with the node E. In that case, it is clear that the nodal value or the value of the conductivity at the face E should be the same as the conductivity at the node value of E. So in that case, we can now write, and similarly when we go to point P, when the face E is taken to point P or is taken close to point P, the value at this interface should be determined more by P and not by E. So we can write Ke as Fe into Kp plus 1 minus Fe into Ke. So this is an linear interpolation of conductivity between points P and E. Also note that in this formulation, if Fe is half, then we get Ke to be the arithmetic average of conductivities at point E and P. Right, so if the face E is midway between points P and E, we get an arithmetic mean. So this formulation is the arithmetic mean form of approximating conductivity at point P. Now, even though this approach is extremely easy to understand, there are huge issues, there are severe problems with this formulation. One of the major issues with this formulation is that it cannot handle this abrupt change, especially when we spoke about this composite slab, right? A non-homogeneous material. So in case, let's say you have a non-homogeneous material, so let's say we have two materials put in contact with each other. And now let's say we have a grid and we're trying to solve for temperature distribution in these materials. So let's say point P is here and point E is here, and this also happens to be our interface for the control volume. So this is some material B, this is material A, and Ka is not equal to Kb. Okay. Now in this form, we know that there is an abrupt change in conductivity. So we have, if I can plot the conductivity with maybe white color is a good option. So let's plot K versus, so on this axis we can say is K, and of course on this axis is space. So the conductivity would have some value till here, and then it may actually show a change, sudden change, right? So conductivity would change suddenly at this interface. But our formulation of this of averaging will say that the conductivity at this point, at this phase E here, would actually be some average value. And so clearly that would actually give you a wrong assessment of the flux crossing this boundary. Okay, so what we need is a formulation that will actually give a better representation of flux crossing such an abrupt or such a sudden change in materials. So what can we do? So the solution lies in the way we wrote the flux at this phase E. So we wrote flux at KE, or flux at E, as KE into TE minus TP by delta XE. Right? This is how we were writing the flux. And this flux will actually lead us to the correct value of, or a more physically realistic value of KE. So let's say we solve a steady state problem. One D analysis with no heat generation. In that case, between nodes P and E, we could write the flux as Tp minus Te, right? Tp, I'm sorry, I think this is, sorry, just notice this is Tp minus Te. Yeah, that's a flux. So Tp minus Te by delta Xe minus, remember this is this distance here will be delta Xe minus, and this distance is delta Xe plus, right? So this is still here and this is still here. That is basically by an electrical circuit analogy, we can write that the flux should be, sorry, this is Kp and this is Ke. So now if you compare these two equations, what we get is delta Xe by Ke should be the same as delta Xe minus by Kp plus delta Xe plus by Ke. And if I divide the whole equation by 1 by delta Xe, right, what we'll get is 1 by Ke to be, now remember delta Xe plus by delta Xe was defined as Fe, so we'll get 1 minus Fe by Kp plus Fe by Ke. Further, let's say Fe was half or 0.5, then Ke would become 2 times Kp Ke by Kp plus Ke, which is essentially the harmonic mean of Kp and Ke. Now one of the key features of harmonic mean is that, let's say, as an example, to illustrate my point what this actually means, if let's say we just take some values, let's say Kp is 1 in some units and Ke is, let's say, 10, then Ke would actually be 2 into 10 into 1 by 11, which is 20 by 11, which is, let's say, nearly 2. So the harmonic mean actually gives a value of the property which is more closer to the lower value. However, the arithmetic mean would have given me Ke to be half of Kp plus Ke, which would become 5.5, right? And this is basically halfway between both these values. So it is quite clear that this value is much lower as compared to what the arithmetic mean will give me. And before I discuss whether this is correct or not, let's also go a few steps further. If Ke is given by this equation, so let's say this is what our equation for Ke would be eventually, and this is what we end up using, then this generalized expression can be used to write what should be the coefficient Ae in the discretization equation. Remember that Ae was Ke by delta Xe. So that means if I put that expression for Ke, which is going to be 1 minus Fe by Kp plus Fe by Ke raised to minus 1 into 1 by delta Xe. So what we should get is Ae would be delta Xe minus by Kp plus delta Xe plus by Ke raised to minus 1, which is the conductance of the material between points P and E. Now I can also obtain a similar expression for Kw and A capital W. So the point to notice is, or the point to discuss is this harmonic mean approach more effective? Right, so is a harmonic mean a more effective approach? So we can answer this using two very basic scenarios. So these are special scenarios. So if the scheme follows, or if the scheme gives accurate answers or an accurate representation for these scenarios, then it is expected to give more accurate answers for any general scenario. So let's look at two extreme cases. Let's say that Ke is nearly 0. So the material at node E has almost 0 conductivity. And it could be homogeneous material as well. So you could have a temperature where the K value at that temperature is almost going to 0. Now in this case, Ke should effectively be 0. Right? Because E, the material at point E, is acting like an insulator, or it's an adiabatic boundary. So effectively the flux going in there should be 0. Now if you look at the harmonic mean, we will get Ke in the harmonic mean will also be going to 0. So this is ideally. Now we're looking at the schemes. So harmonic mean, so this is because E is an insulator. So the harmonic mean will lead to Ke going to 0, clearly. If you look at the general expression again, right? If you invert, or if you look at this equation itself, right? So if Ke is going to 0, that means clearly Ke should also be going to 0. So So if k small e is going to 0, k capital E is going to 0, then k small e would also be going to 0. But the arithmetic mean will fail, because that will give you a value which is mean, or which may be half of the value at point P. That is first scenario. Let's look at the second scenario. Let the Kp value be much more than Ke, but Ke is not 0. So this is sort of like saying that you have a highly conducting material, right? You have a very highly conducting material, and then suddenly it changes into a regular material. So if I could again plot K, right? So one material is extremely conducting, so very high conductivity, and the second material, and this is basically going towards infinity. So I'm plotting K versus X, and there is a node P here, and this is our so this is a node P here, and this is node E. So the conductivity is changing from a large value to maybe a finite value. So in this case, what would we expect? Now if I look at this equation alone, right, now the harmonic mean will give me Ke of 2 Kp K, or I should write in terms of more general form. So if Kp is, so we'll get 1 by, right, so we'll get 1 minus Fe by Ke, rather by Kp, plus Fe by Ke raised to minus 1. So if Kp is much more than Ke, then this term would be nearly negligible, and so we'll get Ke by Fe to be effectively as Ke, right? Now what does this imply? What this means is that the interface conductivity at this point is independent of the value at point P, right? It is solely dependent on value at point E, but it is not equal to Ke. And so first of all, it is not dependent on point P. That makes sense, because the heat conduction or the material here in this region will offer negligible resistance to heat conduction. So the temperature there should actually be nearly constant. So if I can now plot the temperature, right? So temperature is this function. The temperature there would be nearly constant, and it should actually change here inside this material, right? And this is our phase E. That is first part, that this seems to be logical, that Kp or Ke is independent of Kp. The second important aspect that you should now note is that the arithmetic mean will again fail. And it is now logical, because the arithmetic mean will give me again a large value of conductivity at this point, right? So arithmetic mean will actually say that it is the average of these two values, so somewhere here, and that's again not correct. So this would be the arithmetic mean value. Now the third part, and the more interesting part, is that we say Ke is Ke by Fe, and not that Ke is equal to Ke. Now how do we explain this? Now this can be understood if I look at the flux again. So if you look at flux QE, which is Ke into Tp minus Te by delta Xe, right? So this flux right, should be equal to, so we are saying this is equal to, because Ke becomes Ke capital E by Fe into Tp minus Te by delta Xe. Now if you look at this product, Fe into delta Xe, right, this becomes Fe into delta Xe, if you now remember, should be delta X, or it becomes delta E Xe plus. So clearly what it implies is that this formulation accepts, or it is taking into account, that effectively the flux that should be crossing, or the temperature at this location, it's taking into account that the temperature at this, let me take it by red, the temperature at this location here is effectively equal to Tp, right? So it's taking into account that Tp is nearly equal to Te, and so the conduction, the flux leaving, should effectively be equal to Te small e minus T capital E. Or rather, it's taking that, I should not say that, but it's taking that the flux should actually have a resistance, which should be given by, so resistance to conduction should be given by delta Xe plus by Ke, and that is the reason this is again justified. Okay, so to summarize, this harmonic mean approach handles these abrupt changes. Okay, it handles abrupt changes in the conductivity very well, without the need for an excessively fine grid. The second aspect is that even though we did all this analysis based on no sources or non-zero sources, and without talking of how conductivity varies with temperature, this approach also works very well when you have, or it works very well as compared to the arithmetic mean approach when you have, or with, when you have non-zero sources and a continuous variation of conductivity. And so in this course, or in these lectures, we will be exploiting this key aspect in the future lectures when we start doing some basic coding with finite volume method. Okay, so I'll close this lecture here. It's been a long lecture, but I hope you had got a sense of some of the key aspects related to the one-dimensional heat conduction equation. In the next lecture, we'll look at non-linearity of the governing equation, and also the method of source term linearization, and from then on we'll go into two-dimensional finite volume problems. Okay, thanks for listening. Thank you.